In today's video, I will represent some key points about thermodynamics and kinetic stability. Most of the students are stuck in this topic. The purpose of making this video is to see clear that what is thermodynamic and kinetic stability. So let's start. Now you see these two diagrams, where first diagram indicates thermodynamic stability, and second diagram indicates kinetic stability. Both diagrams is the plot of energy versus reaction progress. And S is stand for substrate and P stands for product. Here in first graph, you can see that the energy of P1 means product is more than the starting material means substrate, which is indicated that the product is more stable than the substrate at room temperature. That's why it is known as thermodynamically stable product. Mostly, thermodynamics controlled reactions are slow, because we want a stable product. And you may know that the formation of stable product is slow process. I hope you can understand this first graph, which is the graph of thermodynamic control. Now we move to the second graph, which is indicated the kinetic stability, where you can see that the energy of P2 product is less than the substrate, which is indicated that the product is less stable than the substrate at room temperature. That's why it is known as kinetically stable product. Important thing is that the kinetic product always stable at lower temperature. At higher temperature it converts into thermodynamic product. So let's see the examples. So the first one is thermodynamic stable compound. It's okay, no doubt. But how to identify this? It will also identify by natural stability of molecules. I think one question is came in your mind is, what is the natural stability? It is the stability which is gained by molecules by hyperconjugation or by rearrangement or by inductive effects or by resonance effect extra. So in first two examples, first one is thermodynamically stable, because there is resonance, or, in other word, we can say that there is a conjugation is present, known as alpha-beta unsaturation. But, in case of second compound, there is conjugation is absent, and it is less stable. That's why it is kinetically stable molecule. Now you can see these two alkene molecules, where first is substituted by methyl group, and second is substituted by hydrogen atoms. So the first one is stable, because all methyl group is electron donor, and I think you know that alkene is electron withdrawal group because it has more S character than alkene molecule. That's why this alkene molecule is stabilized by this 2-methyl group, and it becomes thermodynamically stable. And second one is kinetically stable because there is no methyl group substituted. Now let's see last two below examples. Where in first example, the cyclohexene pi bond is more substituted compared to second molecule. So it becomes thermodynamically stable molecules, and second is kinetically stable molecule. I think one question arises in your mind, that is which base gives thermodynamic product, and which base gives kinetic product. So let us move ahead to next slide. Now you see in this slide, there are two class of bases. One STT1 list of bases gives thermodynamic enolates. Oh sorry, because I use word enolates, I think you must know that base will abstract the proton and form anion which is rearranged to form enolate. So the bases, like sodium ethoxide, potassium hydroxide and potassium tertiary butoxide etc., which is unhindered base, called as inorganic base which gives thermodynamic enolates. And base like LDA, LiHDMS, triphenylcarbanion, LiCa etc., gives kinetic enolates. Finally, we will learn about thermodynamic and kinetic stability. Hence, at last, I have homework for you. Now see this slide. Your homework is that you have to prepare the thermodynamic and kinetic analyte of this starting molecule. So I end my video here. If you like this video, then subscribe the channel and share this video with your friends.